early as the Stone Age, humans likely were already using some physical measures of microbial control to preserve foods. Drying, dissection, and salting, osmotic pressure, were probably among the earliest techniques. Nowadays, the physical measures used to control microbes include heat, filtration, radiation, low temperature, high pressure, desiccation, osmic pressure. A visit to any supermarket will demonstrate that heat-preserved canned goods represent one of the most common measures of food preservation. Heat is also usually used to sterilize laboratory medium and glassware and hospital instruments. Heat appears to kill microorganisms by denaturing their enzymes. The resultant changes to the three-dimensional shape of these proteins inactivate them. Heat resistance varies among different microbes. These differences can be expressed through the concept of thermal death point. Thermal death point is the lowest temperature in which all the microorganisms in a particular liquid suspension will be killed in 10 minutes. Another factor to be considered in sterilization is the length of time required. This is expressed as thermal death time, TDT, the minimum length of time for all bacteria in a particular liquid culture to be killed at a given temperature. Both TDP and TDT are used for guidelines that indicate the severity of treatment required to kill a given population of bacteria. Decimal reduction time, DRT or D-value, is the third concept related to bacterial heat resistance. DRT is a time, in minutes, in which 90% of a population of bacteria at a given temperature will be killed. The average thermal death time varies between the microbial types. For example, the higher temperature, the less treat time is needed for kill the non-spore-forming bacteria. Fungi spores need 90 minutes to be killed at 76 degrees. Non-enveloped viruses need higher temperature and longer length of time than enveloped viruses. Moist heat kills microorganisms primarily by coagulating proteins or denaturation, which is caused by breakage of the hydrogen bonds that hold the proteins in their three-dimensional structure. One type of moist heat sterilization is boiling, which kills vegetative forms of bacterial pathogens, many viruses and fungi and their spores within about 10 minutes, usually much faster. Reliable sterilization with moist heat requires temperature above that of boiling water. These high temperatures are most commonly achieved by steam under pressure in an autoclave. Here is a figure demonstrating an autoclave. The entering steam forces air out of bottom, blue arrow. The automatic ejector valve remains open as long as an air-steam mixture is passing out of the waistline. When all the air has been ejected, the higher temperature of the pure steam closes the valve and the pressure in the chamber increases. Autoclaving is used to sterilize culture media, instruments, dressings, intravenous equipment, applicators, solutions, syringes, transfusion equipment, and numerous other items that can withstand high temperature and pressures. The higher the pressure in the autoclave, the higher the temperature. For example, when free-flowing steam at a temperature of 100 degrees is placed under pressure of 1 atmosphere above sea level pressure, that is about 15 pounds of pressure per square inch, PSI. The temperature rises to 101 degrees. The relationship between temperature and pressure is shown in the right figure. Heat requires extra time to reach the center of solid materials, such as canned meats, because such materials do not develop the efficient heat-distributing convection currents that occur in liquids. Heating large containers also requires extra time. This table shows the different time requirements for sterilizing liquids in various container sizes. Sterilization times in the autoclave include the time for the contents of containers to reach sterilization temperatures. For smaller containers, this is only 5 minutes or less. but for a 9,000 ml bottle, it might be as much as 70 minutes. Please keep in mind that liquids in an autoclave boil vigorously, so their containers usually are filled only up to 75% of capacity. In the early days of microbiology, Louis Pasteur, the famous microbiologist, found a practical method of preventing the spoilage of beer and wine. Pasteur used mild heating, which was sufficient to kill the organisms that caused the particular spoilage problem without seriously damaging the taste of the product. The same principle was later applied to milk to produce what we now call pasteurized milk. The intent of pasteurization of milk was to eliminate pathogenic microbes. It also lowers microbial numbers, which prolongs milk's good quality under refrigeration. Many relatively heat-resistant bacteria survive pasteurization, but these are unlikely to cause disease or cause refrigerated milk to spoil. The classic holding method of pasteurization is 63 degrees for 30 minutes. Now, most milk pasteurization today use temperature of at least 72 degrees, but for only 15 seconds. This treatment, known as high-temperature short-time (HTST) pasteurization, is applied as the milk flows continuously past a heat exchanger. Milk can also be sterilized, something quite different from pasteurization, by ultra-high temperature (UHT) treatments. A small volume of fluid spread into an atmosphere of high-temperature steam of 140 degrees for 4 seconds. The fluid is rapidly cooled in a vacuum chamber. The milk can be then stored for several months without refrigeration. Another simple method to destroy non-spore-forming pathogens by boiling at 100 degrees for 30 minutes. Proof boiling, even at high altitudes, will kill most pathogens. The use of boiling to sanitize glass baby bottle is a familiar example. Intermittent sterilization method is also called subsection sterilization method. In the absence of high-pressure sterilization equipment, the sterilization object is relatively stable. The purpose of almost complete sterilization can be achieved. Generally used for liquid sterilization, the method is to heat the liquid to be sterilized at 8 degrees to 100 degrees for more than 15 minutes to 1 hour to make the vegetative cells die. Then cool it to 30 degrees and keep it at this temperature overnight. And this time, the spores in the sterilized sample germinate into vegetative cells because of the suitable temperature. On the next day, the liquid is put in the environment of 80 degrees to 100 degrees for more than 15 minutes. If repeated 3 times, all the microorganisms in the liquids can be killed to achieve the purpose of sterilization. Sterilization in an autoclave is most effective when the organisms either are contacted by the steam directly or are contained in a small volume of aqueous, primarily water, liquid. Under these conditions, steam at a pressure of about 15 psi 101 degree will kill all organisms and their end spores in about 15 minutes. Normal autoclave condition would not destroy prion, which needs 4.5 hours and a temperature of 132 degrees centigrade. Sterilizing the surface of a solid requires that steam actually contact it. To sterilize dry glassware, bandages, and the like, care must be taken to ensure that steam contacts all surfaces.